Hi, everyone. Welcome to Chapter 4. In this chapter, we're going to be describing bivariate numerical data. So, an icebreaker, let's talk about the 3 Ps. We have to look at something personal, professional, and peculiar. Something personal, but not too personal. Something professional, something related to the academic interest, and something peculiar. So, that's just an icebreaker. Now, what is the objective of this session? The objective of this session is to be able to explain the difference between statistical relationship and a causal relationship. So therefore, the reason or the difference between correlation and causation. We wish to interpret the values of the correlation coefficient, the slope of the least square regression line, and when appropriate, interpret the least regression line. We're going to be assessing the usefulness of least square regression using the standard error, SE. So SE stands for standard error. Standard error. And then we have R squared, our linear correlation coefficient, and a residual plot. So we're going to be using these strings right now. These terms seem vague to you, but as we talk about this chapter, we're going to be understanding what this is. By the end of this chapter, you should be able to explain why is it risky to use a least square approximation regression line to make a prediction for values of the predictor variable outside the range of the data. And we're going to be describing the effect of influential observations of an equation of a least square regression line. So what we're going to be doing is we're going to approximate a line using a linear regression or a least square regression line. Let's begin this chapter by discussing what is correlation. The definition of correlation is a bivariate data set consists of measurements or observations consisting of a variable x and y. When both x and y are numerical variables, each observation is a pair, such as 14, 5.2, 27.63, 18.9. When investigating the relationship between two numerical variables, we look at a scatter plot of the data is the best way to start. So when we have only one variable, we usually, of a numerical type, we do a dot plot. Now, when we have two variables and we're trying to investigate the relationship, we want to start with drawing a scatter plot. So remember, when we're doing a scatter plot, there are different points scattered all over the place. And each dot is an XY value. It's a pair. So we wish to look at the scatter plots in figure 4.2 and consider the following questions. Does it look like there's a relationship between the two variables represented in each scatter plot? Is there a relationship? Is the relationship linear? To answer the first question, look at the pattern in each scatter plot. Notice that in the scatter plot, there's no obvious pattern. The points appear to be scattered at random. In this case, we would conclude that there is no relationship between the two variables. Well, look at this one. Notice that if I make a line, it looks like the points are increasing. They're having like an upward slope, an upper variable. Now here, so the part A, we notice that there's a correlation. Now this one, not necessarily linear. It looks like it kind of goes up and down. Yes, it's kind of going upward at an upward pace. Now, look at the next relationship. There's some points over here. They're more kind of scattered all over the place. Definitely not linear. Because if I put a line here, there's not a lot of points that will cross that line. And then 4.2, letter E, the points are kind of scattered. So there's not really a linear relationship here whatsoever. Well, look over here, letter B. Now here, I notice that most of my data lives in this region. So then this would have a skewed distribution. Something skewed because most of my data lies over in this region. So all of the other scatter plots in figure 4.2 show some sort of pattern. So then what can we notice? We can notice that the patterns in the scatter plots of figure 4.A and B are roughly linear, so the first few. So here we have A, and then B. Where's B here? I don't see B. There should be a typo. This one's B. This looks a little bit B. And then C, not linear. E, and then look at B. So B, most of them are in this data. So if we create a distribution, most of it is going to be near the center. Now C and D have some curvature. Now that's just looking at the scatter plot and doing a rough approximation on how it looks like. Now what we see in this table, we're able to identify if there exists a correlation or relationship. And we were able to kind of categorize and summarize them in this data. Tannin concentration and astringency rating. Is there a relationship? Yes. Is the relationship linear? Yes. The mean blood levels and the brain volume, is that a relationship? Yes. Is it approximately linear? Somewhat, yes. Now, in letter C, is there a relationship? Yes. It doesn't have to be linear. The relationship doesn't have to be linear, but there's definitely some correlation there involved. Is it linear? No, because there's some curvature attached to it. Now, letter D, the age and the average finish time, there exists a relationship, but again, it's not linear. And E, there does not have a relationship whatsoever because all of the points are scattered around. And if there's not a relationship, well, then there's absolutely nothing. There's no linear component there. The direction of a linear relationship can be either positive or negative. So you can have a linear correlation relationship to be positive, meaning that all of the points are tending somewhere up, and then you can make a line that looks linear going up. That would be a positive correlation, positive linear. And we can have a negative linear correlation where your points kind of start here. Let me go this way. They start up here and then they kind of go downward. So this would be a negative linear correlation. A negative linear correlation. If a positive linear correlation, that means that as the larger values of x, you will have larger values of y. And if you have a negative correlation, then you start high and then you go low. When this is the case, the linear pattern in the scatter plot slopes upward when you move from left to right. Now, which of the scatter plots in 4.2 suggest a positive linear correlation relationship? Look over here. Well, here we have a positive correlation on that first one because all of the points seem as my x value increases, my y value increases. So 4.2a would be a positive linear correlation. So the scatter plot in figure 4.2 shows a positive linear correlation between x and y. The scatter plot 4.2b shows a negative linear correlation. That would be the last one here because I start high and then I go low. So see how all the points become negative as my x value increases. Next, consider the 4 scatter plots in figure 4.3. So now we're going to see other 4 scatter plots. These scatter plots were constructed using data from graphs in paper. So what we're trying to look at right now are general patterns in these plots. All 4 of these patterns were described by showing positive linear correlation. The line shows in each scatter plot was used to describe the linear relationship between x and y. Look at the first one. As x increases, my y will increase. So this shows a positive linear correlation relationship. Next one here. This also has a positive C, but now look, this one is a little bit less linear because it doesn't really reach all of the points. Same thing here. There's still increasing as my X is increasing. And last but not least, here D, they're still crossing some points, but not all. When the points in the scatter plot tend to cluster tight around the line relationship, then we say that the relationship is strong. So here, notice that the relationship is not that strong because it doesn't really touch a lot of the point, D or C or B, but A does. A has a better because they're kind of clustered towards the line. If they are clustered close to the line that we have, that would make a linear correlation stronger. So try order which one shows the strongest relationship to the weakest. So we just talked about that. For which of the four is the most information between X and Y? Well, we saw that A, C, B, and D, that's the order. So letter B and C are pretty close. But now we talk about something called the correlation coefficient. So the correlation coefficient is a statistic, so it's referring to a sample that can be used to assess the strength and direction of a linear relationship. So when we are looking at these cases, so look at D. D has a good approximation, not so much C, and then also B. So then for sure, we would say that A has the strongest, and then C, and then B, and then D. Now, when it can be difficult to judge the strength of a linear relationship just by inspection, just by viewing the graph, it's better to actually calculate something called the correlation coefficient, or R. That's where we introduce the variable R. So Pearson's sample correlation coefficient, denoted R, measures the strength and the direction of a linear relationship between two numerical values. Remember, R can be greater than 0 or positive, or R can be negative, depending on what we have. Let's first investigate some general properties of R. Let's consider 4.4, which shows 8 different scatter plots and the associated value to the correlation coefficient. So R will be given, and we're going to be identifying, okay, well, what's the value of R? So the first scatter plot, we see that R is 1. Well, if we make a straight line, notice that it's very strong. It actually will be all of the points. So the value of R is equal to 1. The second scatter plot, R is 0.97. So it's not exactly perfect, like 1, but it's very close. R now is 0.70. So notice that as R is decreasing, the less strong correlation we're going to have. R is 0.35. So if I'm trying to do a positive, it's every time the points become further. Now look at this. What happens when R is equal to 0? The points are scattered. There exists no correlation, no linear correlation. So the correlation coefficient is R. When R is 0, you don't have a correlation. Now what happens when R is negative? Negative 0.26. Look at the correlation. It's negative. Now it's going to go somewhere downward, but it shouldn't be touching a lot of the points. Negative 0.75, how strong it is. But now it's going in the opposite direction. Now this is a perfect line, but R is now negative 1. So what can we identify? So as R decreases, or R is bounded between negative 1 and 1, where 1 is the strong positive correlation, so R equal 1 is the strong correlation, R equal negative 1, strong positive. Negative 1 is the strong negative correlation. And then we can have points in between. R less than or equal to 1. So what happens when R equals 0? There's no correlation. No linear correlation. So the correlation coefficient value R measures the strength and the direction. When R is negative, it's going to go have a negative correlation. If R is positive, we're going to have a positive linear correlation. Again, as the value of R increases, the correlation becomes stronger. As R decreases, it becomes weaker. So what would be the largest possible value of R? R would be 1 because 1 is the exact positive correlation as a perfect linear correlation. The smallest value of R would have to be -1. Now my graph is going to go downward instead of upward. So you have a negative correlation. If R is negative 0.7 and R is 0.7, which has a stronger linear correlation, actually will have the same correlation. Why? Why will they have the same? They will have the same because the absolute value, so when they're just going to have, it's the same linear relationship, just different direction. Different direction. One is going to go upward, one is going to go downward, but the strength of the relationship is going to be the same. Now look at one more scatter plot shown in figure 4.5. The correlation coefficient R is 0.038, which is very close to 0. Because R measures the strength of a linear relationship, this indicates that there's not going to be a linear relationship between the age and the finish time. The scatter plot, however, shows a definitely non-linear pattern. So when R is near 0, you should not conclude that there's no relationship, but there is less of a linear relationship. So be sure to look at the scatter plot to see if there is or not a linear relationship. Now look at this one. This is 4.5. The scatter plot shows a strong but not a linear. So this one, it would be a curved relationship, but not a linear. And you can definitely have that. So now, by looking at the scatter plot and correlation coefficients in figure 4.4, you should now have discovered the most general properties of R that follows. Now, these are the properties that we have to learn and identify. The sign of R matches the direction of the linear relationship. R is positive when the linear relationship is positive and negative when the linear relationship is negative. The value of R is always greater than or equal to -1 and less than or equal to +1, as I mentioned above. So R is bounded between -1 and 1. The values near the upper limit, 1, indicates a strong positive relationship. So if you're very close to +1, you have a strong linear relationship. If you're close to -1, then you have a strong negative linear relationship. Figure 4.6 shows a useful way to describe the strength and linear relationship based on the value of R. It may seem surprising that the value far away from 0 as -0.5 or 0.5 is in the weak category. Now we're going to talk about that later in the chapter. So if you're halfway, you're not that close actually, because you want to be very close to +1 and -1. All right, everyone. So just reminding you that when R is equal to 1, only when all of the points in the scatter plot fall on a straight line, that the slope is upward. Similarly, if R is equal to -1, then that means that only when all of the points fall on a downward slope line. R is a measure of an extent to which x and y are linearly related, that is, the extent to which the points in the scatter plot fall close to a straight line. Even if the value R is close to 0, there still will be a strong nonlinear relationship. The value of R does not depend on the unit of measurement for either variable. So for example, if x is a height, the value of R is the same whether the height is expressed in inches, meters, or miles. So it does not depend on the unit. Now here we have a scale where it represents where does the value of R lie. If it's past 0.8, then that's considered a strong correlation, strong linear correlation. If it's in between 0.5 and 0.8, it's considered a moderate linear correlation. If it's anywhere between -0.5 and 0.5, that is weak. after negative 0.5, it's a moderate, strong negative correlation, and a strong negative correlation if it's between negative 0.8 and negative 1. So this is a good scale to kind of decide what is considered a strong correlation, what's considered a weak, and what's considered a moderate. The first step in calculating the correlation coefficient is to calculate a z-score for each of the value of x by subtracting x bar and then dividing it by s of x. So x minus x bar over s of x is the z-score. Next, calculate the z-score for each of the y values. So we would have to find a z-score for both x and y. So here are the formulas. X minus x bar over s of x, y minus y bar over s of y. So we would have to first find the mean of x, the mean of y, and then take each independent x value subtracted by the mean divided by the sample standard deviation of x, the sample standard deviation of y. Then use the formula in the following box to calculate the value of r. The linear correlation, or the correlation coefficient r, is calculated using the following formula. R is going to be the sum between the product of z of x times z of y over n minus 1. The product of zx times zy is found by multiplying z of x and z of y for each observation in the data set, and then adding z of x and z of y values. Let's start by writing this out. Another way to calculate the linear coefficient correlation R is that we'll also be able to use the calculator. So this is using z-scores, where remember z of x will be x minus x bar over the standard deviation of x, and z of y is going to be y minus y bar over s of y. Oops, let me bring this a little bit upward. So y minus y bar over s of y here, the standard deviation of y. Now, as more expensive, let's do an example. Let's start doing an example and calculating the linear correlation R for a particular example. Does it pay to pay more? Does it pay to pay more for a bike helmet? Are more expensive bike helmets safer than less expensive ones? Data on X is the price in dollars. Y is the quality of the 50 different brands. And we are going to be constructing a scatter plot in figure 4.9, and the data is used from the Consumer Reports website. The quality rating was the number from 0 as the worst possible rating to 100 as the best, and was determined to using the factors included in how well the helmet absorbed the force of an impact, ventilation, and ease of use. Now this is the figure, and then notice that what's the pattern? It looks like we're going to have a linear correlation, right? Because as R progresses and Y progresses. So this is the information of the scatter plot. We are interested in looking at the appearance. The appearance, there's not a lot of a linear relationship between price and quality, but we are going to find the value of R. Value of R was given in this example. R was 0.073. Notice that when we were looking at the data, so what happens when R is 0 and then negative 0.5, 0.5, and then 0.8, and then negative 0.8. Where is this is the weak part. And notice that the value 0.073 falls in this region, in the weak region. So Minitab is another website, another format that you're able to calculate R. And you're going to be doing it using your calculator, or R is going to be given. But based on the data, we notice that 0.073 is inside the weak region. A correlation coefficient R of 0.073 is very close to 0, and it indicates that there's not a noticeable tendency for higher quality of ratings associated with higher price helmets. So in fact, inexpensive helmets actually have a high quality rating. So that would be our interpretation. So it doesn't really make much of a difference if you pay a very expensive helmet versus a non-expensive helmet. Now, how the correlation coefficient measures the strength of a linear relationship. The correlation coefficient, what it does, it measures the strength of a linear correlation by using z-scores. And why? Because z of x minus x bar over s of x. Remember, when we're looking at a z-score, we're looking at a position, measure of the position. We saw that and we learned that in chapter 3. Now, values that have larger x bars will have positive z-scores, and those with smaller x bars will have negative. Also, y values larger than y bar will have positive linear correlations, and those smaller will have negative z-scores. Keep this in mind as you look at the scatter plot in section or figure 4.10. What do we see here? So this is our diagram, viewing a scatter plot according to the signs of c of x and z of y, a positive relationship, a negative, and a not so strong. So if we kind of cut this in half and we want to look at the correlation, well, what do we see here? Well, here we don't really see any of those points, but if we break them in quadrants, this first quadrant, z of x is positive, while z of x is negative, and the product between z of x and z of y is negative. Now, in this region, quadrant 1, z of x is positive because it's above. So here, x is greater and y is less than, let me see, x bar and y bar. Here we have the values of x are large than x of bar. Let me see here. So here we have x being greater than x bar. Here y is z of y is negative, so then y is less than y bar. And then the product, of course, now here, if z of x is positive, that means that x is greater than x bar. Z of y is positive, that means that y is greater than y bar. Z of x times z of y are both positive. Now the second, if z of x is negative, that means that the value of x is less than x bar. Here, if z of y is negative, positive, it's y is greater than y bar, and the product is going to be negative. Now here, z of x is negative. That means that x is less than x bar. Z of y is negative. Y is less than y bar, but the product is positive because two negatives give you a positive. So that means that letter A over here, these points over here, have a positive relationship. B will have a negative relationship. So let's look at B. B looks like it's going to have a negative relationship. And then C, what do we notice about C? It doesn't have a strong relationship because if I notice that the points are more scattered. So as I'm moving forward here, look at the value of x bar. If x bar, and then here what happens as this line, who's bigger, and then we have a y bar. So let's see if I over here, oops, let me make this a different color. So here we have x bar. Over here we have y bar. So if we look at these points right here, we notice that here, this value x is greater than x bar. Same thing here. Now look at the value of x and the value of y. Y will be negative. Y would be less than y bar. So depending on where we are, now if x is above or x is below, let's look over here. X is going to be greater than x bar, and y is greater than y bar. So those points up here. But the point are that they're kind of scattered all over the place. So the linear correlation coefficient R will not have a strong relationship. So a value of R close to 1 indicates that larger values of one variable tends to be associated with the larger values of the other variable. This does not mean that a large variable of one will cause the other one to be large. Be careful. Correlation measures the extent of association, but association does not imply causation. Okay, correlation does not associate with causation. It frequently happens that two variables are highly correlated, not because of the change in one, but because they're both related to a third variable. Check your understanding. Consider the following questions. So we are going to be doing a discussion post here. Where is R.6? What does it mean when R is equal to 0? What happens when R is equal to 0.7? Explain why the correlation coefficient of 0 does not necessarily mean that there's not a relationship between two variables. Be careful there because R is strictly linear. So there can be a relationship, it will just not be linear. And with that, we finish 4.1. Let's go over to section 4.2. 4.2 talks about fitting a line to a bivariate data. Now we would learn how to find R. Now we're interested in finding a line of a bivariate data. When there exists a relationship between two numerical variables, you can use information about one variable to learn about the second variable. For example, you might want to predict Y as a product of sales for a month when the value of X is the advertising 10,000. So if you know one variable, the independent variable, you can find the response variable. The letter Y is used to denote the variable you would like to predict, and this variable is called the response variable or responsive variable or the dependent variable. So response variable is also the dependent variable. The other variable denoted by X is called the predictor variable or the explanatory variable or the independent variable. So X is the independent or the explanatory, where Y is the responsive or the dependent variable. Now, when we wish to find a line and linear relationships, we usually use this linear equation, y equal a plus b of x, where a is the intercept of the line and b is the slope or the pattern. The value of b is called the slope of the line, is the amount in which y increases when x increases by 1 unit. The value of a is called the intercept or the y-intercept, or even the vertical intercept of a line is the height above the value of x is equal to 0. So a is the point 0, a, where x is going to be 0, and a is going to be your vertical position, or the y-intercept. Choosing a line to summarize a linear relationship, the principle of least squares. So the first thing we want to do is we want to make sure we have a scatter plot. Consider the scatter plot shown in figure 4.13a. This scatter plot shows a positive linear relationship between x and y. You can think about this using a line to summarize this relationship. But what line should you use? Two possible lines are shown in figure 4.13b. Is it easy to choose between these two lines? Line 1 provides a better fit for these data. Let's look. So this is A. Yes, we can create a line. It looks like it's going to have a positive linear correlation. It looks like it's going to have a strong linear correlation. So we have line 1 and line 2. So what does it look better? Does it line 1 or line 2? Well, how many times does it touch more times? The points touch more in line 1. So line 1 seems to be the most appropriate. Now, what about line 1 or line 2? It's actually difficult because see how line 2 are more clustered around line 1. So you're looking for the points that are more clustered. Which of the two lines in 4.13 are closer? What would be the better choice? And it looks like it's going to be, they're approximately the same, but it looks like, so if I draw line 2, let me erase the colors here. So if I'm looking at line 2, and the points are kind of scattered in line 2 versus line 1, you're trying, here's a choice that isn't too obvious, right? It's hard to determine which one is the line of best fit. To measure how well a particular line fits, you can use the vertical deviations from the line. There is a deviation for each point in the scatter plot. To calculate the deviation between x and y, we're going to be substituting